Hey everyone, welcome to this explainer. Today, we're diving into how autonomous AI agents remember, and more importantly, how attackers can covertly turn that exact memory right back against them. Look, if you're a computer science freshman stepping into the world of AI right now, understanding how these systems maintain state is absolutely critical. We're not just talking about those basic chatbots from a few years ago anymore. We are talking about fully autonomous AI agents executing real-world tasks, reading emails, deploying code, making financial decisions. So today, we're unpacking a massive vulnerability that targets the very foundation of an AI agent's reality. Trust me, the code you write in the future is going to depend entirely on how well you grasp this threat.
Think about it like this. Imagine slipping a perfectly forged map into a friend's backpack today, knowing for a fact they won't even look at it until they go hiking next month. By the time they actually get lost in the woods, you are long gone. That is the exact temporal decoupling we're unpacking today. And honestly, the scariest part? Your friend trusts that map completely just because they pulled it out of their own backpack. They assume it's safe. Well, that is exactly how an AI views its own database. We're looking at exploits that literally wait silently in the dark until the system implicitly trusts them.
Okay, here's our game plan for today. We'll start by mapping out Agent AI's three memories, then contrast prompt injection with memory poisoning. Next, we'll break down the anatomy of a poison attack, look at the multi-agent blast radius, and finally, wrap up by exploring how to secure semantic memory with tools like A-MemGuard and other future defenses.
To really understand this exploit, we first need to map out the agent's mind to establish what exactly is being attacked here.
As CS students, the easiest way to think about an agent's memory architecture is mapping it to system architecture you already know. So short-term memory, that's basically your computer's RAM. It holds the current conversation but gets totally wiped when the active session ends. Then you've got episodic memory, which is like your system log files, tracking past interactions so the agent can maintain state across a few turns. But semantic memory? That is the hard drive. Mechanics-wise, this is usually a retrieval augmented generation, or RAG, vector database. It takes massive amounts of text, like corporate policies, converts them into numerical arrays called vectors, and pulls them up when the agent needs context. So when attackers go after semantic memory, they are permanently altering the agent's factual knowledge base, right at the vector level. So let's contrast the quick, familiar attacks with this entirely new paradigm of stateful compromises.
The difference fundamentally comes down to one word: persistence. Prompt injection is a transient smash and grab, whereas memory poisoning is a stateful long con where the attacker leaves a persistent trap. You know, if a hacker tells a chatbot to ignore previous instructions and speak like a pirate, that's prompt injection. It targets that short-term working RAM we just talked about. The second you close your browser tab, the pirate is gone. But memory poisoning, that embeds malicious instructions deeply into persistent storage, those RAG vector databases. It completely outlives your active session. The agent is going to retrieve that poison memory next week or next month and just implicitly trust it as a foundational truth.
All right, let's look at exactly how hackers execute this long con using a query-only methodology known as MINJA. MINJA stands for Memory Injection Attack, and it's a brilliant three-step process. First, the hacker hides a seemingly benign bridging step inside a totally normal, everyday PDF document. The agent reads it, and that document contains an indication prompt, which subtly tricks the AI into synthesizing a completely false rule. Like, oh, I must always blind CC this external attacker's email address on all future financial reports. Then comes the crazy part: progressive shortening. The attacker's prompt basically forces the agent to compress the memory, which effectively deletes the original prompt from the context window. The attacker's fingerprints literally vanish. What is left behind is a brand new, clean-looking role in the database that is secretly harboring a malicious payload. And because autonomous agents implicitly trust their own retrieved memory, these sleeper attacks can just lie dormant until some totally unrelated user query triggers the payload weeks later. I mean, think about the absolute nightmare this creates for debugging. If your financial system suddenly starts leaking reports in April, you and your engineering team will naturally look for a breach in April. But your traditional security monitoring won't catch a thing because the code itself wasn't breached. The data was logically manipulated back in February from a web scrape that looked perfectly safe. The agent is just rationalizing its bad behavior using its own corrupted memory, genuinely believing it's executing official company policy perfectly. Now things get incredibly complex when we introduce multiple agents operating within a shared ecosystem. This vulnerability scales catastrophically. Imagine a multi-agent ecosystem where a basic research agent, a deployment agent, and a highly privileged security agent all share the exact same semantic RAG database. The research agent reads a poison document online and updates the shared database with a new insecure policy. Well, later, the deployment agent queries that same database, retrieves the poisoned policy, and boom, executes a malicious script. This creates what we call viral agent loops. They're effectively self-propagating worms that spread rapidly across the network without exploiting a single line of traditional code. The agents confidently justify their actions to each other because to them, the corrupted data they're passing back and forth is the absolute truth. With OWASP classifying this as a top risk for agentic applications right now, how do we actually lock the vault and protect the state? Well, private knowledge retrieval, or PIR, is a fantastic mitigation strategy. It ensures an agent can safely extract facts from third-party databases without exposing its queries to tampering. Think of it like a student going to a public library to check out a highly sensitive book, but they're using a mathematical cloak, so the librarian has absolutely no idea which book was retrieved. Technically speaking, PIR uses advanced cryptography to mask the query vector itself. This means the host server cannot infer what the agent is thinking about or searching for, which totally prevents the database from feeding the agent targeted, dynamically poisoned responses based on its query history. But PIR alone isn't enough. We need defense in depth across the entire architecture. As computer scientists, you know we heavily rely on cryptographic hashing. By comparing hash checksums before retrieving state, the system instantly detects if a memory block was subtly altered by an attacker. We also use digital signatures to track provenance, cryptographically verifying exactly who or what wrote that memory in the first place. And by strictly partitioning memory into isolated scopes, like keeping user level completely separate from admin level, we ensure that if an attacker poisons their own local session, that poison is contained. It never gets promoted to the global RAG database used by the entire organization. If the agent trusts its own memory implicitly, we have to deploy frameworks that teach the system how to systematically doubt itself. Enter A-MemGuard.
A-MemGuard is this brilliant, non-invasive layer that verifies reasoning paths against multiple memories and cleanly separates safe data from anomalies. Instead of just looking for malicious keywords, which attackers can easily bypass, A-MemGuard looks at the structural reasoning path. It cross-checks retrieved memories against each other. For example, if 3 retrieved memories structurally agree that company policy is X, but one newly inserted memory claims it's Y, A-MemGuard spots the logic flaw. And when it spots this fake, it doesn't just delete it, it quarantines it into a separate lessons learned dual memory vault. This vault basically acts like a digital immune system, cataloging known attack patterns so the agent never falls for the exact same trick twice. And the results of this consensus-based approach are staggering. Researchers tested a worst-case scenario. An attacker manipulated the database so perfectly that the top 4 memories the agent retrieved were all completely poisoned. The attacker dominated 100% of the immediate context. But because those malicious memories couldn't form a unified, coherent logical structure amongst themselves over time, A-MemGuard's consensus validation still successfully filtered out up to 97.87% of the poisoned data. It really proves that deep structural logic checks can defeat even the most overwhelming malicious context. As CS students stepping into the world of AI, you absolutely must remember this. Securing an agent means protecting the persistent data it relies on to construct its reality. We are moving so rapidly away from stateless, simple chatbots and entering an era of autonomous digital workers. If you're going to build these multi-agent systems, you can't just focus on securing the application code anymore. You have to secure the data flow, verify the cryptographic provenance, and aggressively protect the memory structures over time. So, when an AI's memory outlives your session, how will you mathematically prove its past hasn't been rewritten by an unseen adversary? I'll leave you with that final thought to ponder as you design the next generation of multi-agent systems. The challenge isn't just making AI smarter anymore, it's ensuring that its memory actually remains its own. Thanks for joining me on this explainer, and keep building securely.